everyone, welcome to another Project Advice video. So today we'll be looking at discrete random variables. So as always, I'll just give a bit of advice first, then go through the actual content itself, the questions, before finally giving a summary of what you should be memorizing for this chapter. So some general advice is that usually we will use capital letters to denote the actual random variables themselves, but then we will use lower case letters for the values that they actually take. So a random variable can have a certain value depending on what you want. And in that case, that's why we will use a capital letter for the variable itself and then a lowercase letter for the true value. Then when we are making our random variables, the thing is that we can give it any letter we want. But we try to avoid using certain letters like Z, B, P, and N because these are terminologies for other stuff. So and you'll learn it later. And we'll be learning about this thing called expectation as well as variance. But actually expectation can mean the same thing as mean also. And try to score for this chapter because usually it's quite routine, so you can score a lot of marks for this chapter. So this is our content. Just give an introduction first and the definition of what a discrete random variable is. The difference between discrete and continuous, before showing what is a cumulative function, finding the probability as well as the expectation and variance and standard deviation, as well as binomial, which is a big part of this chapter. So an introduction to random variables. Suppose when we toss two dice, what are the few possible outcomes that we can measure? So we can measure things such as the number of ones obtained, the number of given outcomes, or the sum of two dice. So for instance, when we are tossing a pair of dice, we are often interested in the sum of the two dice and are not overly concerned over the value of each individual die. So there are different scenarios as to how you can get, let's say, a sum of 7. Can be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, or 6, 1. In fact, some of them are mirroring each other or be in a different order. So a random variable is ultimately a quantity whose value just depends on chance. Like in the game of Monopoly, the number of steps moved in one turn is considered discrete. It is because there is a clear number of steps between the possible values you can take and the possible values you cannot. And so probably the capital letter will represent the variable itself, while the small letter represents the value which this variable can take. So another experiment is that we toss a pair coin 3 times. And what pair coin means is just 50% heads, 50% tails, and observe the outcome. Then you can represent the sample space as ohm in this case. Then it can be like heads, tails, and so on and so forth. So if we let x be the random variable denoting the number of heads obtained when tossing a pair coin 3 times. This x, which happens, is the random variable for this experiment. And the possible values that x can take is like 0, 1, 2, or 3. And so the value assumed is of course subject to chance. And so if we are saying Px equal 2, this refers to the probability of x containing 2 heads in the 3 tosses. So after this chapter, you also learn another chapter called continuous random variables. And so the difference between discrete and continuous is that a discrete random variable takes on a countable number of possible values, while a continuous random variable can take on any value in a given range. This can be a 1, 4.20, or minus 15. But with continuous, there's no exact end to what value it can be. So it can be like the number pi or even your really, really exact height. So down to the smallest measurement possible. And so these are some examples of what is discrete and what is continuous. The number of phone calls a person picks up in a minute is discrete because you can only count from like 1, 2, 3, 4, 5. But the lifespan of a light bulb manufactured by a factory, you can never really measure definitively either. Because it depends how precise you want to do your measurement. Then the number of students who are late for school on a particular day, because you are counting people, it's possible to be discrete because you can't have half a person. Then the distance traveled by car in a week is again continuous because you cannot measure precisely. And the height of a student from a class will also be considered continuous. So then we'll look at cumulative distribution function. So if x is a discrete random variable with probability mass function for Px equal x for x equal x1, x2 all the way to xn, then the cumulative distribution function is given by fx, where fx is basically the sum of all the probabilities before and up to x. So yeah, it will just be a summation of all the probabilities. So you start with px equal x1 plus px equal x2 all the way until you got x. So this example, this is a table showing a pair die. So if you want to find the cumulative distribution function, this is going to be finding the sum of the probabilities up to a certain score. So in the case of F1, it just means the probability that x equals 1, which in this case is just 1 over 6. But if you want F2, you take the probability of x equals 1 and x equals 2, sum it together, you get 2 over 6. The same can be said for if x is less than or equal to 3, x is less than or equal to 4, and so on and so forth. And in the case of 7 and 8, that is already 1 as well, so you cannot really go beyond it. So you can think that there's also a range for this cumulative distribution function, that it will always be between 0 and 1, like all the other probabilities you calculate for other questions in general. So another question, let S be the sample space of the experiment, such as the outcome of tossing 3 coins. So we let X be the random variables defined to take values of the experiment, the number of heads. So a table or formula can be giving the values of X. And this is called the probability distribution. So if we sum up all these probabilities together, you'll all be equal to 1 over all the values of X in S. And this is a powerful insight, as you can use this idea to help you find unknown probabilities. So let's say that we don't have the probability for let's say x equals 2. If we know the 1 over 8, 3 over 8, and 1 over 8, we can take 1 minus all these other probabilities to find the unknown here. So that is what we can do for some of the questions that you'll see later in the video. So an example is that for biased inequalized, the probability of any particular score between 1 and 6 inclusive being obtained is inversely proportional to that score. So find the probability of scoring a 2. So that what this means basically is that scoring 1 is 6 times as likely as scoring 6. So we're going to create an unknown representing these different proportions and scale it to each dice value. And through that, we are able to see basically if we sum everything together and then we solve it, we can find out what this proportion is. And by knowing this proportion, we can then apply it to finding a probability of scoring a 2. So that's exactly what we did, and this is how we came about to 10 over 49. Then now we are going on to expectation. So the expectation, or mean or expected value, of a discrete random variable x is the weighted average of the possible value of x can take on, each value being weighted by its corresponding probability. And basically what this means is that if you have a larger probability, then that value it takes will have a greater significance in the calculations. So it is denoted by EX or mu, and it's a measure of the center of the probability of x. So formally, if x is a discrete random variable taking values from a set x, then the expectation of x is basically the summation of x times the probability of itself. So when you do all that, you can get the expectation. So this is just an example. The probability distribution of a discrete random variable is given by p1 equals y, where if y equals 0, the probability will be 1 over 10. But in the case of it being 1, 2, 3, or 4, there's a certain probability and is proportional to a certain constant. So given that c is a constant, find this value, and when you find the value finally, find the expectation. So when we are creating a summation, we are going to have an upper limit of 4 and a lower limit of y equals 0. So this is what we do. We're going to take our value y times the probability of itself. So this is how we get 1 over 10 times 0. Wait, 1 over 10, just 1 over 10 plus c plus 4c plus 9c plus 16c equal to 1. Or in other words, 1 square c, 2 square c, 3 square c, 4 square c, all this is equal to 1. Then we will use that to find the value of c. And after that, when we find the expectation, we will just take the probability times the actual value itself. So this is how you get 0 times 1 over 10. And then you do the summation of 3y squared over 100 from 0 to 4. No, from 1 to 4. And that's how you get an expected value of 3. So there's a certain relationship between expectation and sample mean. So let's consider the number of heads obtained when we plot 3 fact points. Denoting the number of heads obtained by x, the possible values that x can take is either 0, 1, 2, or 3. By working out the values of x equals 0, 1, 2, or 3, the probability distribution of x is presented in the following table. So if we want x equals 0, it's just going to be tails times tails times tails, which is in other words, it's just half times half times half, which is 1 over 8. Then likewise, you can do the rest of the calculations for 1, 2, and 3. So based on the probability distribution, the expectation, or in other words, a summation of x times the probability of itself from x equals 0 to x equals 3, as those limits will lead to 1.5. So, but the thing is that if you actually toss a 3 coin, like let's say 50 times, and observe the number of hits obtained in each of those tossers, the data obtained can be represented in a table known as the frequency distribution. And you notice that actually the frequency may not always correlate to the actual expected result. So you see that instead of 0.125, we get a 0.1, or like a 0.375, we get 0.4. So there's not always like a direct value and exact figure when doing our experiment. But the thing is that what we know is that if we increase the number of tosses to n times, where n is large, we will expect the result for the relative frequency distribution to be close to the result of the probability distribution. Then the expected value of x can be well approximated by the sample mean, since the result for relative frequency distribution would be close to the result of the probability distribution. So in general, we have the following properties. So if we let x and y be random variables and a and b be constants, the expected value of a constant will be the constant itself since there's no variability. Then in the case of the expected value of EAX, it's just going to be a times the expectation of the value of x. Then if you have, let's say, ax plus b, it's just going to be a commutative law. We just build on the first two principles themselves. So it's just going to be aex plus minus b also. Then in the case of eax plus by, you can also just split it as per usual with the other three properties. So a function of a random variable itself is a random variable. So if x is a random variable, then we have a function such as cosine x, x squared, or 2x plus 4, given x minus ex squared. These can also be considered random variables. So if in addition x is a discrete random variable, then every function of x is a discrete random variable also. And so the expectation of this gx, where g is a function of x, can also be obtained as follows. So it's just going to be the summation of whatever value you get out of the function times the probability of that value of x as well. So the expectation g, where g is a function of x, can be obtained as follows. So it will just be, let's say we want to find expectation of x squared. It is going to be the summation of x squared times the probability of getting that value of x itself. So it will be like 0 times 0.4, 4 times 0.3, 16 times 0.3 to get 6. So what we did is that instead of using the x value, we find x squared and we use those values instead in our summation to find the expected value. So the discrete random variable has a probability distribution given by x equals 3x plus 1 over 21, or equal 1 to 3. So find the expected value of log x. So what happens is that we are gonna take the probability and then find the value times the log x also. So that's why we have log x, log 1 first, times 3 plus 1 plus 1, 3 times 1 plus 1 over 21, plus log 2 times 3 times 2 plus 1 over 21, so on and so forth. And then because log 1 is equal to 0, that's why our final answer is just going to be a simplified version of the two expressions. It should be 1/3 log 2 plus 10 over 21 log 3. And on to variance, which is the second part of a discrete random variable. So the variance of a discrete random variable x is a measure of the expected spread of a random variable about its mean. So in the case of a discrete random variable, the variance can be given by the expected value of x minus the mean squared. So in other words, it's just the summation of x minus the mean squared times the probability of getting x itself. Then the standard deviation, which is what a lot of you guys learn in secondary school, is basically similar to variance, but we take the variance and we square root it to get our standard deviation. So consider the probability distribution of these two random variables x and y. By symmetry, both the expected value of x and expected value of y is going to be equal to 3 because the probabilities on like either side of 3 are both like very similar to each other. The 1 over 50 for py1 equal y, py equal 1 is the same as py equal 5. Then likewise for the random variable x, it's just a uniform probability distribution of 1 over 5 throughout. But the thing is that when we are calculating the variance, there will be a difference. So the formula for calculating variance, besides the previous one, is that you can take variance equal the expected value of x squared minus the ex all squared. So what happens is that we will take 1 times 1 over 5 plus 2 squared times 1 over 5 plus 3 squared times 1 over 5 plus 4 squared times 1 over 5 plus 5 squared times 1 over 5. Then we minus our ex, which in this case is 3, all squared. So it will be 11 minus 9 equal to 2. Then the same applies to the variable y. You take 1 times 1 over 50, 2 square times 4 over 50, so on and so forth. You get that minus your 3 square again. In this case, it's 9.32 minus 9, which equals 0.32. So there's a difference. Even though x and y have the same expectation, their variances are different. This is because the variability of the variance of x is large, as the observations of x are widely scattered from the mean, whereas the variance of y is small, as observations of y tend to cluster close to the mean. And it's because the probability of py equals 3 is 4 over 5, which is quite significant, whereas the values of like py equal 1 or py equal 5 is not very small and quite minuscule in comparison. So in general, for discrete random variables, we have the following property. The variance of a constant is, well, a constant, so it's 0. Then when we have like a variable, and this constant affects the variable, so ax, you will end up getting a square variance x. In the case of variance x plus minus b, the thing is that the constant doesn't add to the spread at all, which is why it can be ignored, and it's basically the same as the variance of a itself. Then if x and y are independent variables, then the variance of a plus minus by, we again like there's a commutative law where you can spread them apart, and you get a square variance x plus your b square variance y. Then the variance of x plus y is just going to be the variance of x plus the variance of y summed together. So notice that the variance of a constant is 0, and this is because this is expected as a constant has no variation. Then for two random variables x and y to be independent, the events described by x and y must be independent. So if it's not independent, we cannot use this formula, and instead we have to do something else, which usually the question will provide some input as to how you are supposed to calculate it. So here's an example. Find the variance of x in this case given the probability distribution. So likewise, we are just going to go find ex, and we're going to find ex all squared. So can then find ex squared, which in this case is just going to be 2 square p plus 3 square p plus 4 square p, I mean the 1 minus 2p. Then you simplify it, you'll get 16p minus 17. So then we can find our final variance, which is going to be ex squared minus the all square of ex itself. So if you do that, it will simplify and you'll eventually get minus 9p squared plus 40p minus 33. So then the next part, which is what you see for a lot of your questions, is binomial distribution. So by definition, a binomial experiment is an experiment consisting of n trials, each with two possible outcomes which may be regarded as either a success or a failure. Additionally, the probability of getting a success and subsequently failure at each trial remains constant, and the trials are independent. Then we call such experiments binomial experiments. And so, questions may ask you what are the following properties or like things that make you sure that what you are testing is a binomial experiment. And so these are the three main things. One is that it consists of n independent trials and the keyword is independent. The outcome of each trial only has two outcomes. Either it's a success or a failure. And the probability for each such trial is denoted by p, where this probability has to be constant. So one example will be the coin toss, because it can either be heads or tails. So when we toss a coin 10 times, you'll either get heads or tails. So if we got getting a head as success, and we are using the same coin, the probability of success will be constant because these tosses are independent of each other. The coin doesn't change after each toss or anything like that. So that's why we can say that the coin tossing experiment is considered a binomial experiment. But if we are going to draw 5 cards from a deck of playing cards and we do not have replacement, then we cannot regard this as a binomial experiment, because if we consider the outcome where each draw of a success is when the card draw is the king and the failure is not, such an experiment will not be binomial as it violates the first property. And what is first property is that they are independent draws. The thing is that after each card draw, there will be less cards in the deck. So from 60 we count 59, 58, 57. And what happens to that is that the probability will change. And so this means that you will lose, or like there will be our dependence on each outcome. So that's why you cannot say that they are independent trials. And so this will in as not a binomial experiment. But if there's a replacement of cards, there will be 5 independent trials and a constant probability, which in this case will become a binomial experiment. Because then you have a constant probability and each draw will not be affected by the previous one. And so a binomial random variable. The random variable x denoting number of successes in the n trials of a binomial experiment It's called a binomial random variable, and it can take on values from 0 all the way to n. And so the probability that x takes the value x, denoted by px y, depends on the number of trials, as well as the probability of success. And so the probability distribution of a discrete random variable is called the binomial distribution. And we call n and p the parameters of the distribution. We can then write our binomial random variable, which in this case is x, squiggly line, b, bracket, n, and p. So the random variable x representing the number of hits obtained is a binomial random variable, and how we can write it is that we know that our n value is 3 and the p value is 2 over 3, so that's how we write it. We put our 3 there first as the n, then our p will be the 2 over 3. So, for example, a coin is biased such that the probability of obtaining a hit when a coin toss is 2 over 3. The coin is tossed 3 times, so if x represents the number of hits obtained, find px equals x for x equals 0, 1, 2, 3, and tabulate the probability distribution of x. So, the plan is that we're going to consider the different scenarios to get x equals 0, 1, 2, 3. We're going to find the probability, and then after that, with all the information, we can then draw out the table. So in the case of x equals 0, that means 3 tails. So in this case, there will be 1 over 3, 0 equal 1 over 27. And for the case of x equals 1 and x equals 2, there's different ways you can get your heads or tails. It can be the first coin, the second coin, the third coin. So that's why you get the 3 choose 1 and the 3 choose 2. Then we have our 1 over 3 and our 2 over 3s with the relative powers over there. Then lastly for 3 heads, it's just going to be 2 over 3 to the power 3, and that's how we get our 8 over 27. And so what the probability distribution table will look like is on the right hand side over there. Here another example. So in the UK, the failure rate for treatment by IVF is 70%. Find the probability that there are exactly 6 failures in 15 randomly chosen patients receiving the treatment. And given that there are fewer than 8 failures in the 15 treatment, find the conditional probability that there are exactly 6 failures. So we know that the n value or the number of samples will be 15. Then the probability of success in this case is going to be 70%, which if we convert to a normal number is 0.7. So with that, you can then go to your graphing calculator, and when you use your graphing calculator, you can then just put all the numbers in. You get when px equals 6, a value of 0.11590, which in this case you will round off to 3 significant figures, which is 0.0116. Then for the second part, this is conditional probability, so it falls back on your probability chapter as well. It's going to be px equals 6, given that x is less than 8. So what happens is that we're going to find the scenario where both happens, divide by the probability that you get x is less than 8. So we're going to do that. The numerator is just going to be x equals 6 itself. Then the bottom is just going to be anything where x is less than or equal to 7. So when you do that, you'll end up getting a probability of 0.232. So if x, b, and p, where x denotes the number of successes in n trials for a binomial experiment, then the probability distribution of x is given by px equals x, where it is n choose x times the probability of x times 1 minus the probability n minus x, where n choose x is just n factorial over n minus x factorial x factorial. All this can be found in your MS26 as well, and this is called a binomial distribution with parameters n and p. And so the mean, or else the variance and expectation, all these can be given by Ex equals the number of samples times the probability, while the variance is similar to the expectation. It will be number of samples times the probability of success times 1 minus the probability, so like the anti-probability. So that's how you can find both the expected value and the variance, both of which can be found in the MS26. So a binomial random variable x, for example, has a mean of 1 value and a variance of 1 value. Evaluate the parameters of the distribution, given that another independent variable y, such that y is a binomial random variable with n20 and p is 0.1. Find the probability that x plus y equals 6. So we're going to look at x first and try and break it down. So based on the previous slide, where ex equal np and variance equal np minus p, we actually insert this value inside and see what we can find. So if for np, which our ex is equal to 1.2, and our variance x is np 1 minus p 1.08. We can then solve it together by substituting our 1.2 into the 1.2 and 1 minus p equal 1.08. By doing that, we can find out that p equals 0.1 and then our n is equal to 12. So that's how we can find our parameters for the binomial random variable of x. Then since x and y are independent, as they say in the question, that means they have the same probability of success. No, that doesn't mean they have the same probability of success. But in this question, it does. They will have a probability of 0.1. We can add them together, and so what happens is that the n will just be the sample value of x and the sample value of y combined together. You get 32. So in this case, x plus y is just going to be a binomial random variable with n equals 32 and p equals 0.1. So if you want to get px plus y equals x, we just take those values, put it into the GC, and we'll end up getting 0.0585. And so that is what the graph of probability distribution table of a binomial random variable looks like. And in general, as x increases, the px equals x will increase to a maximum value, after which it will then decrease. Yeah. So it's kind of a peak mountain. So now to the different questions that I came across. So these different life scenarios, this is just some of the questions or different cases where I've seen the way that DRV is being tested. So I'll go through each of them as follows, give a step-by-step rundown of the solutions for each of them and what is the solving methodology for each question. So the first one is quite simple, just asking you to find the expected value and the variance. So in this case, when a tetrahedral die is thrown, the number on the face, which is length x, has the following probability distribution. It's given that ex equals 2.5 and variance of x equals 1.25. So tabulate the probability distribution of d, the random variable representing double the number of the die lengths. So then afterwards find ed and variance of d. Then tabulate the probability distribution function of s, the random variable representing the sum of two numbers when the die is shown twice independently. Then find the es and the variance of s. So for part 1, it's just going to be finding d. So what we do is that the probability of d is exactly the same as the probability of x. What changes is that instead of 1, 2, 3, 4, we're just going to multiply by 2. So it becomes 2, 4, 6, 8. So after drawing this probability distribution table, then we know what the different values of d are and then what it can take out. So by doing that, we can then find the value of ed. So we can just take 1/4 times 2 plus 4, 6, 8, all that. Then we get 5. And another way you can do it is by symmetry. Notice that they're all symmetrical and evenly distributed. So you can see that the middle number in a way is also 5. Then to find the variance of d, we will find ed square first. So in this here will be 1/4 times 2 square and plus 4 square plus 6 square plus 8 square equal 30. Then the variance will just be that 30 minus 5 all square equal 5. Which actually equal to 2 square variance of x. You don't need to express it as 2 square variance of x, but I want to show something later. Just bear that in mind, there's 2 square variance of x. Then for s, they say that they want the sum of two numbers when the die is thrown twice independently. So we can actually draw like a giant 5x5 grid. The sides will have the 1, 2, 3, 4, 1, 2, 3, 4. Then in the remaining 4x4 grid, what we are going to do is that we're going to show all the different scenarios that s can take on. So if you get 1 and 1, the sum is 2. Then likewise, you can show the scenarios for what value you get from the lowest value 2 to the largest value 8. By doing that, it will be quite easy to draw out the actual probability distribution table and see what are the probabilities that s can take on whatever value from 2 to 8. So after you do this, you can then find the expected value of s and the expected value of s squared. So in this case, it will be 1 over 16 times 2 plus 6 plus 12 plus 20 plus 18 plus 14 plus 8 equal 15. Then es squared will just be 1 over 16 times 2 squared plus what's that? 18 plus 48 plus 100 plus 108 plus 98 plus 64 equals to 27.5. Then to get the variance, it's going to be es squared minus that's not correct. will be ES squared minus the all square of ES, which will be equal to 2 variance of X. So actually you notice that there's some difference here in terms of the results. So they will have the same mean. So ED is equal to ES, which is equal to 2EX. But then is that the variance is different. So when we found the variance of G, it's actually 2 squared, which is 4 variance of X. For the variance of S, it's going to be 2 variance of X. So the variances are the same. Variable D actually has a larger variance. Yeah. So that's the difference between when we multiply by 2 or when we just find the sum of 2 random variables. So yeah, that's the difference, and that's why even though it can look similar, there can also be some different results. So that's the difference you have to bear in mind between addition and multiplication. Then scenario 2 is finding an unknown k probability. So sometimes the probabilities will be unknown and you have to find it first. So in this case, 4 rods of length 1, 2, 3, 4 units are placed. The probability of selecting a rod of length L is KL. Find the value of K. Then find the expected value and the variance. Then if a second rod is selected, find the probability that value of X plus Y is equal to 3. So to solve this question, what we need to do is that we need to list out the sum of the probabilities, which we add all the probabilities together, which will be equal to 1. We can then find it and then solve K. Then after we get K, we can then find out the EX and the variance X. And then with all that, we are able to find the probability that Px plus Y is equal to 3. So we have K plus 2K plus 3K plus 4K equal 1. That would be mean 10K equals to 1. So K is 0.1. Then we will find EX and EX squared. So in this case, EX is just 1 times 1 over 10 plus 2 times 2 over 10 plus 3 times 3 over 10 plus 4 times 1 over 10 equals 3. Then the variance will be EX squared minus the all square of EX will be 10 minus 3 squared, which in this case is equal to 1. Then if you want to find the probability that EX plus Y equals 3, we're going to look at the different scenarios. So the values that X should take are 1, 2, 3, 4. So that means there's 2 scenarios. Either X equal 1 and Y 2, or X equal 2 and Y equal 1. So when we do that, we put the probabilities inside, we will end up getting a final answer of 17 over 360. Then another question will be finding the minimum samples n to get a certain probability. So in this case, what it can mean is that a discrete random variable X denotes the number of sixes showing when 2 ordinary factors are shown. Calculate the probability distribution of X, and then 2 tries are thrown repeatedly. Find the probability that if I throws, the result X equal to occurs at least once. And given that the dice throws n times, find the least value of n such that X equal to occurs at least once in the n throws. So what this means is that okay, ignore the scenario 3. What it means is that we're going to find a probability that X equal to occurs. What this means is that we are going to get 2 sixes in a row. So if you want X equals 0, what that means is that we don't get the 6 at all. So we avoid the 6, we get like a 1, 2, 3, 4, 5, which is how we get 5 over 6 squared because we want it to apply to 2 dice. Then for X equals 1, we want it to be 1 dice is 6, so we get a 1 over 6. Then we get something that isn't 6, so in this case, how is it? There are 2 scenarios, so it can be on the first die or the second die. So that's why we have to multiply by 2. Then for X equals 2, it's just going to be getting that 1 over 6 for that specific 1 6 square to apply to both dice. So yeah, we let Y be the random variable denoting the number of throws where 2 6s appear out of 5. So in this case, it'll just be Py is greater or equal to 1. Because what we're doing is just going to be 1 minus the probability that there are no scenarios where there are 2 6s appear out of 5 throws. So in this case, it will be 1 minus 35 over 36 all squared equal to 0.131. So notice that when we want to do the second part, the dice is drawn n times. What actually happens is that we can replace our 35 over 36 power 2 with power n to resolve the second part. And so what happens is that we're going to let W be the random variable denoting the number of throws 2 6 appear out at throw. So likewise, we want to find the same probability. 1 PW greater or equal to 1 be greater than 0.9. So I will express the PW greater than or equal to 1 in terms of 1 minus 35 over 36 power n, where basically 1 minus PW equals 0. In doing so, we can then solve it simpler by making it n ln 35 over 36 by applying log to both sides. Bring the 1 over to the other side, the 35 over 36 power n to the other side. We then find a way to make n the subject, which in this case will mean that n is greater than 81 over 7, which therefore means that the least value of n is 82. And why we switch the signs is that ln 35 over 36 is less than ln 1. And because it's less than ln 1 means that it's negative. So that's why we can switch the probability signs. For this question, during our mathematics lesson, Ms. Jane wanted her viewers to build a model. She carried two indistinguishable boxes of bricks into class. The bricks are identical and indistinguishable except for colors. The number of color bricks is in the table below. So our pupil wants to draw two bricks from these boxes to build a model. He draws a brick randomly from one of these boxes. The brick is not replaced, and he then draws a second brick randomly from one of the boxes. It asks you to find the probability that it does not draw any yellow brick. Then asks you to find the probability it does draw two yellow bricks. Then tabulate the probability distribution table of the yellow bricks. So that's the first part. So for this first part, the key thing to know is that they never specify whether you draw from box 1 or box 2. So this is why they wanted to, in a way, have this show part so that you know how you're thinking for this question. Because there are several scenarios. So in this kind of scenario, you can simulate whether they are picking whether it's box 1 or box 2, or box 1 both times, or box 2 both times. So that's how we can simulate the four different scenarios. So yeah, for this question, we're going to let x be the random variable, denoting the number of yellow bricks drawn. So if you want to have the probability that no yellow bricks are drawn, that means we need to have either something from red or blue 1, and then another from red blue from box 1. Or we can have a red blue from box 1, and then another red or blue brick from box 2. So this is basically what I'm trying to say when we decide the different scenarios. Sometimes we will take the red or blue bricks from box 1, or we will choose from box 2. The key idea is that as long as we pick from a box, it cannot be a yellow brick. So that's how we get the different probabilities that are shown. You write down all the different probabilities for each one, add them up, and that's how you will get the 25 over 72. So yeah, in terms of finding each probability specifically, like for example, probability that a red or blue from box 1 and then another red or blue from box 1 is going to be half, because there's a probability of half whether you take box 1 or box 2. And then after that, you do 5 over 10 because 2 plus 3 red and blue bricks is 5. Then after that, you draw one. That means one less red or blue brick and then one less brick in the box in total. So 4 over 9. Do the same for the other three scenarios also. So yeah, that's how we get the probability that he does not draw any yellow brick is 25 over 72. Then for part 2, they want to find the probability that he draws 2 yellow bricks. So in this case, you can also play out the different scenarios. It can be box 1 first, box 2 second, or box 1 both times, box 2 both times, or mix and match here and there. So again, you do that. So it'll be half times 5 over 10 times half times 4 over 9, plus half times 5 over 10 times half times 3 over 10, plus half times 3 over 10 times half times 5 over 10, plus half times 3 over 10 times half times 2 over 9. So basically what we're trying to do is that the first set is for box 1 first. Then the second one is a mix and match. The third one is also going to be a mix and match before the final one is going to be solely on box 2 doing both draws. And that's how you will get the 53 over 360. Yeah. Then afterwards, they ask you to tabulate the probability distribution table. So for the last one, P(H2 we actually don't need to calculate the different scenarios because like I said before, we already have P(x) equals 0 and P(x) equals 2. So what we can do is that since the sum of all these different probabilities is equal to 1, we can just take 1 minus these two probabilities to get our P(x) equal 1, which in this case is just going to be 91 over 180. Then they ask you to calculate the expected value. So in that case, we'll just take x times the probability of the x itself across all the different possible values of x. So 0 times 25 over 72, 1 times 91 over 180, plus 53 over 180 times 2, which will give you 4 over 5. Then for the next part, Ms. Kim decides to combine the two boxes of bricks into a single box. Donald draws 5 bricks with replacement from the single box. Find the probability that he draws less than 2 yellow bricks. In this case, we're going to let W be the random variable denoting the number of yellow bricks drawn out of 5. So this will make a binomial distribution. We have 5 bricks and the probability we get the yellow is going to be 8 over 20. So the probability that he draws less than 2 is just going to be as such. So it's just going to be PW less than or equal to 1, which in this case will be 0.336, which will round up to 0.337. Yeah. And for part 5, Donald wanted to build a model with a yellow brick. He randomly draws a brick until he finds a yellow brick, and this is with replacement. So find the probability that will not take him more than 9 draws to get a yellow brick. So what it means by saying not more than 9 draws is that there are about 9 scenarios. Either he gets on the first draw, second, third, fourth, fifth, sixth, seventh, eighth, ninth. So you will see this question in some similar form in a way throughout a lot of your papers. And although it can seem a bit funny to calculate all the 9 probabilities, actually what I'm going to see is that it's actually going to be a geometric progression. So the probability that you do get a yellow brick is going to be 8 over 20. But the probability that it isn't a yellow brick is going to be 12 over 20. So that's how we get the pattern you can see below. If it gets you on the first draw, it's just going to be 8 over 20. If it's on the second draw, you get 1 minus 8 over 20, which in this case is 12 over 20, times the 8 over 20. And repeat this over and over again until you get to the final term, which in this case is 12 over 20 to the power 8 times 8 over 20. Put this in your GC through a sigma summation and you'll get 0.990. So yeah, for this question, just take note that there will be a lot of geometric progression. So just see the common ratio and you'll be able to solve these questions quite easily. Here, next question is proving the mode of a variable. So for these questions, you have to prove algebraically that the mode of a certain binomial random variable is a certain number, which in this case they want to show is 4. So usually how we do it is that we want to show that the probability of p x equal k plus 1 is greater than the probability of x equal k, or on the other side, the probability that a specific value is greater than any probability value greater than or less than that specific one. So the thing is that there will be a bit of a domino effect. We already saw in the previous question, the previous part, that I can find the graph. The graph not here. Yeah, if we look at the graph here, what happens is that our binomial random variable tends to have a peak. So it's at this peak that we can then infer that anything less than it will be less, anything greater than it will always be greater, no matter what value, because there can only be a single greatest value. So that's what we're trying to look at for this question. So what we're going to do is that we're going to show that px equal k plus 1 over px equal k is greater than 1, because this will imply that px equal k plus 1 is greater than px equal k, and then we're going to find the inequality to find what this k is. So first thing first, we're going to break down what px equal k plus 1 is, as well as what px equal k is. So what happens is that if you look at your MS26, you see that the formula for binomial is that it's going to be 10 choose k plus 1 times the probability of success to the power of n times the probability that it is a failure to the power of the sample size 10 minus the number of times we get the x. So in this case, k plus 1. And for your denominator is also a similar formula. It's just going to be 10 over 10 choose k times 0.4 power k times 0.6 to the power 10 minus k. So we further break it down. We break down what the 10 choose k plus 1 is and what the 10 choose k is. And you realize also that all the powers, like the 0.4, 0.6, actually the numerator and denominator are quite similar to each other. So what we're doing is that we're going to cancel out all the common parts, such as 0.4 to the power k and 0.6 to the power of 10 minus k. And that's what we end up with. Then we further simplify it. You'll see that we end up getting 2 times 10 minus k over 3 times k plus 1. And so after this, we're going to infer that this fraction is greater than 1. Because if we say it's greater than 1, it implies that px equal k plus 1 is greater than px equal k. And then we solve it. We're going to get a probability of, we're going to get a value of k of 3.4 or less. So the thing is that also, what this first implies is that px equal 4 will be greater than px equal 3, greater than x equal 2, greater than px equal 1, px equal 0. The thing is that if we reverse it around, let's say k is greater than 3.4, this would then imply that the fraction above is going to be less than 1. And what this means is that P is equal to K plus 1 is less than P is equal to K, which in this case means that the 4 will be the greatest value. And this means that 5, 6, 7, 8, 9, 10, all the probabilities will be less. So it's in a way just looking at a reflection. So by looking at that, we can then tell that the probability, or in other words, the mode of X is going to be 4. Yeah. Then another question. So sometimes the question will give you their own random variables, and so in that case, we are just going to follow with it. So in this question, we are given that the probability t equals 0 is 1 over 36. The probability that t equals 3 is a quarter, and that t equal 1 equal probability t equal 5 equal a certain probability, which in this case we denote it as p bracket 1. Then the probability of t equal 2 and probability of t equal 4 also equals a certain unknown. And what is unknown is we make it as p bracket 2. So about finding the values of p1 and p2, calculate the expected value of t. So what we're going to do is that we're going to take the summation of probability of t's. It should be equal to 1. And it's going to be 2 p1 and p2s, because we are looking at pt equal 1, pt equal 2, pt equal 3, p equal 4, pt equal 5, all this sum together. So since pt equal 1, pt equal 5 equal p1, we're going to have 2 of those, and likewise the same for p2, maybe plus the 1 over 36 plus 1 over 4 equal 1. So by doing that, we can then find out what pt equal p1 and p2 is, which is in this case 30 over 36. So if we want to find the expected value, it's just going to be the probability times the variable itself. So in this case, it will be 0 times 1 over 36, 1 times p1, 2 times p2, 3 times p4, plus 4 times p2, and 5 times p1, which in this case, fortunately enough, it's just going to be 6 of p1 plus p2, plus 3 over 4, which in this case is equal to 35 over 12, when we substitute our p1, p2 bracket. So that's how we find the expected value. Then next question is quite a large question, and for probability and statistics, I really want 12 30 mark questions. So in this case, this was one of them. So it's quite complicated. So but still quite doable. A 3-step inspection scheme is derived to determine if a box is accepted or rejected. Then there are 3 steps below. That's the process. Find the expected number of bulbs to be tested under this inspection scheme. So what happens is that a random sample of 50 bulbs is tested. And if it contains fewer than 3 defective bulbs, the box is accepted as satisfactory. If there is more than 3 defective bulbs in the sample of 50, then the box is rejected. But if there's exactly 3 defective bulbs, a second random sample of 25 bulbs is tested. If this second sample contains no defective bulb, the box is accepted as satisfactory. But if there's more than 1 bulb in the second sample, then the box is rejected. If there's exactly 1 defective bulb, a third random sample of 25 bulbs is rejected. And if there's no defective bulbs in this last box, then it's considered satisfactory. Otherwise, the box is rejected. So there's quite a lot of permutations that can come about in this inspection procedure. So to find the expected number of bulbs, what actually we need to do is that we need to consider the different scenarios. So we're going to consider what happens if we're going to use 50 bulbs. What happens if we're going to use 75 bulbs, which in this case just means first and a second box. Then we're going to consider what happens when we have to use 3 boxes, or in other words, 50 plus 25 plus 25. So what happens is that for the probability that we use 50, we are going to find the probability that the probability that it is exactly 3. Because if it's exactly 3, then we bring on to the second stage. So what happens is that if we get more than 3 defective bulbs, we already know that it's unsatisfactory, so we don't need to care about it. But at the same time, if we have less than 3 defective bulbs, then we also know it's satisfactory, so we don't need to test for any more bulbs. So that's why for n equals 50, we just need to get rid of the ps equals 3 specifically. And for the case of pn equals 75, what happens is that we need the x equals 3 in the first place so that we can get to the second box. So after that, when we get to the second box, we want to find the case where we don't need to do any more tests. So in this case, it's going to be 1 minus the probability that we go on to the third box, which in this case is going to be pw equal 1. So that's how we get the second probability. Then the third probability, it's just going to be the very specific scenario where we get p equals 3, and PW equal 1. So what this means is that the first box we get exactly 3 defective bulb, the second box we get 1 defective bulb, and whatever happens in the third scenario, the third step, it doesn't matter because either way we're going to use another 25 bulb. So that's how we ended up getting our expected value. So in this case it will be 50 times the probability of Pn equals 50 plus 75 times the probability of n equals 75 plus 100 times the probability of n equals 100. And after all that reading and analyzing, that's how we end up getting to the 50.6. So just be careful with reading all these procedures. But after a while, you'll see that actually it's quite logical thinking. If you, as long as you can get a logical chain of thought, you'll be able to get through these questions quite well. Then another question, which is these last few questions will be binomial. A large number of tickets are sold in a lottery. Each ticket can either win a small prize or a large prize, but no ticket can win 2 prizes. 10% of the tickets will win small prize, while 0.1% of tickets will win a large prize. So if Charlie has 20 tickets, find the probability that he wins at least 1 prize, and find the probability he wins at most 3 prizes. And if Mary keeps buying tickets until she wins a prize, find the probability that she wins her first prize within the first 4 tickets she bought, or partly, she buys at least 6 tickets before her first win. So what we're going to do with the first part is that we're going to create a binomial random variable. So we let x be the number of tickets that can win prizes out of 20. So in this case, our sample size n is going to be 20. Then our probability that we get a success, or in other words win prizes, is 0.1 plus 0.01. Then we're going to find the probability that he wins at least 1 prize. Which in other words just means the probability of everything minus the probability that he gets no prize, which is 1 minus px equals 0, which will be 0.881. Then find the probability he wins at most 3 prizes. This is just going to be px is less than or equal to 3 equals 0.863. Ignore the typo. And then for part 2, if Mary keeps buying tickets till she wins a prize, find the probability that she wins a prize within the first 4 tickets. So this is going to be a new random variable. We're going to let y be the number of tickets Mary buys up to including the ticket which she wins her first prize. So the probability of y less than or equal to 4 will just be 0.347. So this is basically the geometric progression again. So what I mean is that we're going to find a probability that she does get a ticket. She does get a prize on the first ticket. If not, find the probability she doesn't get a prize on first, but she does get it on the second. Then you do the same. Not first, not second, but third. Then not first, not second, not third, but fourth. So if you add all this up, it will be equal to 0.347. Then the thing can be said for py is greater or equal to 6. This one will be the same as 1 minus the probability of x is less than or equal to 5, which in this case will be 0.587. Yeah. And for this last question, scenario 9. The latest operating system OS of the GC is required for the installation of a new application. On average, 3 out of 4 students have the latest OS in their GC. So what happens is that a class of 26 students is to report to their mathematics tutor to install the new application. Find the probability that the 15th student who reports is a 9th student who has the GC with the latest OS, or the last student is a 10th student without the latest OS. So how are we going to look at this question? That it has to be a very systematic matter. We're going to look at the first 14 students first, then the 15 students specifically, then the 16 or 25th student, and finally the 26th student. So we're going to create 2 random variables. Let x be the random variable including the first 14 students, of which how many have the latest OS, which in this case we are going to have sample size of 14, and probability that he does have the latest OS, 0.75. And likewise you do the same for y, but in this case it's going to be the 16 or 25th student. Then, yeah, what this probability stands for is that out of the first 14 students, 8 of them have the latest OS. The 9th student who has the OS is going to be a 0.75. Then from the 16th student and 25th student, we want to find another 7 students who have the OS. Because what we want is that the 10th student without the OS is going to be the last student, the 26th student. So what this implies is that we need to have 16 students with the OS. So 8 plus 1 plus 7 will mean we get the 16 student. So that is why in this case py is equal to 7. Then lastly, 0.25 is for the last student without the OS, which is how we get the 0.25. And by right, the answer should be 0.00344. So that's all I have for the scenarios. Another few things that I picked up is that basically for anything that says all but 1, we can just take 1 minus everything is calculated to get the specific scenario. So in other words, finding a complement. And expectations can be added and subtracted, but periods can only be added. So this means expected value of M minus J is equal to the expected value of M minus the expected value of J, but we cannot do the same for our variance. Then we can check also the ranges to see what is the lowest possible sum and the highest possible sum respectively. You could just be finding one scenario as a result of nothing lower or higher. So in some cases, it's just going to be the same probability of 0, like if you go at very high numbers, for example. Then if there are two variables where x is derived from s, and you let y equal 2x minus 3x, you cannot say that the variance of y is equal to 4 variance x plus 9 variance s because they are not independent. What happens in x will affect s as well. So that's why they cannot be independent. So that's just one example. That's all I have. This is some stuff that you should memorize for DRV. Basically, again, just the different properties of expectation and variance. Over time, these will become rather intuitive, so no need to worry about it. But just know at the back of your mind should be good enough. Then lastly, to find a mode, you just need to show that the probability for a specific value k is greater than any probability of k minus 1 and k plus 1. Because whatever happens, there will be a domino effect, where if ps equal k is greater than ps equal k minus 1, it will be greater than k minus 2, k minus 3, so on and so forth, and as well as k plus 1. Yeah, what is no. Yeah, if it's greater than ps equal k plus 1, it will be greater than ps equal k plus 2, k plus 3, so on and so forth. So that's all I have for this chapter. If there are any questions, you can always PM me if the video is not clear enough or whatever things about your own math or whatever. So yeah, that's all I have for today. Hope you enjoyed the video and hopefully I'll see you in the next one.